Okay, great. So, what have we been doing in the last couple lectures? So, well, the first thing we've been doing is we've been studying the Sylow theorem and some of its consequences. So, the main hypothesis for the Sylow theorem, as we've learned it, is that we have a group, and we write its order as some p to the n m, where p doesn't divide m. And what we found is, by sort of a clever analysis of the group acting on its subgroups of order p by conjugation, is that, first of all, the number of Sylow p subgroups, which instead of denoting L, I'll denote NP of G, because in today's lecture I'm going to want to deal with lots of different things. I'm going to have lots of different primes going on and lots of different groups going on, so it's better to be able to keep track of both of those in the notation. So the first fact we observed was that this thing is congruent to 1 mod p. In particular, Sylow p subgroups exist. Otherwise, the number couldn't possibly be congruent to 1 mod p. And the other part of that was that the number of Sylow p subgroups divides m. And these are really, really useful because in many cases they allow us, this sort of counting thing allows us to figure out exactly how many subgroups of order p to the n there are. And that can be a source, for instance, of normal subgroups if you can show that np of g must be 1 for some p. So the other part, and this is again extremely useful, every Sylow p subgroup or every two Sylow p subgroups are conjugate. This is also very useful. This has some good consequences. So here are some consequences. First one I'll mention is that, with the hypothesis that I have some Sylow p subgroup, first one I'll mention is a condition for normality, right? So we've seen several times that this thing is normal if and only if, as a result of 2, np of g is equal to 1. And this is something you can leverage much, much, much. It's very, very useful. Another thing that's useful is that once you have a Sylow p subgroup like this, you know a good deal about its normalizer. Why? So for instance, what is the index of the normalizer of h and g in G? Any guesses? No. But yes. NP of G, exactly. So why is that? Well, let's just go through a quick explanation just to make sure that this is all clear. This is just the counting formula. So this thing is the same thing as the index in G of the stabilizer. I mean, this thing is by definition the stabilizer of H, where we have G acting on the Sylow p subgroups by conjugation. Right? Is that clear? And we know by a sort of counting formula that this is exactly the number, the size of the orbit of H under this action. And then, well, because of 2 over here, this thing is the same thing as the number of Sylow P subgroups. And this is just by definition NP of G. So this is also a very useful sort of formula, and we're going to leverage this in some of what we do today. And the third sort of consequence, which is very, very useful, it gives you a lot of insight into group structure, is you can count the number of elements of particular orders in some cases as a result of the Sylow theorem. So for instance, and I think you've seen this before, we've seen a certain diagram many, many times before, and it's sort of the intuition behind this. Suppose I can write the order of a group as Pm. So in other words, this thing here is 1. So suppose the group order is Pm, and of course, P doesn't divide M. Then the number of elements of order P in G is what? How many elements of order P are there? So remember, we have if I have an element of order P, then it generates some subgroup, some cyclic subgroup. Now, it's a Sylow P subgroup. Now, all of these are conjugate. And we know exactly what the size of that orbit is. It's NP of G. And the number of elements in each of these things of order P is P minus 1. So the answer is NP of G times P minus 1. Again, a very useful formula because it can help you narrow down what NP of G is, for instance. I mean, there'll be cases where the formula over here, number 1, narrows it down to a bunch of different possibilities. But then what you can do is you can look at lots of different primes and say, well, if it, NP of G were this number, then I'd have this many elements of a certain order, but I also have a certain number of elements of a certain other order, and that's too many elements. The group's too large. So this is, again, a very, very useful but simple observation. Okay, so what were some applications that we have more or less seen of these sorts of things? So this was one of the big early tools in trying to understand structure of groups of small order. You can pretty much get everything you need out of Sylow theory from for deciding what the structure of, or what the different isomorphism classes of groups of small order are. So let's look at some applications that show that off. So first one that we've seen is groups of order PQ, and P less than Q are primes. So what was one of the things that we know about groups of order PQ? I mean, so are there any normal subgroups that are guaranteed in a group of order PQ by the Sylow theorem? Yeah?
I think it was a homework problem that there has to be a non-trivial normal subgroup.
Right. So of which order?
Of order P and one of Q, I would think.
Well, so you're guaranteed one of order Q. You have to be more careful in the case of order P. So let's look at exactly what the right statement is. So just by the counting formula that I just erased here, I know that the number of Sylow P subgroups must be dividing Q, but congruent to 1 mod P. Now, since P is less than Q, that automatically guarantees that the number, I meant to say Q there. So the number of Sylow Q subgroups is congruent to 1 mod Q and divides P. So it's either, getting this mixed up. Right, so, yeah, so, well, yeah, I mean, in either case, yeah, it's It's either Q or 1, and the one that's the one with the more restrictive. Right. So it is Q. So we must have a normal Sylow Q subgroup, because the number of Sylow Q subgroups must be 1 or p, but it also must be congruent to 1 mod q. And since q is larger than p, that automatically guarantees that nq of g is 1. Now, as for the other, so if p does not divide q minus 1, then again, by the same reasoning, you get that np of g equals 1. And so you have a normal Sylow p subgroup. And then it's not hard to see. I think you probably did this, not last lecture, but the lecture before that, that in that case, you just put together your Sylow p and Sylow q subgroups, and you end up with what must be a cyclic group of order pq. The things sort of have an appropriate sort of commutativity there. So you can show that the thing must be abelian. And show that this thing must look like z mod pqz. If p divides q minus 1, then, well, it could still be the case that it's z mod pqz, but it turns out that you can show, and I'm not sure that you did this, but there's a sort of simple construction of a group which is not abelian of order pq. Then there exists a unique non-abelian group of order pq. The uniqueness part is not terribly hard, but it's the more subtle point. It's not hard to construct such a thing. I mean, you can sort of do it by hand by taking pairs of elements of z mod p and z mod q and then sort of defining a funny multiplication operation where you twist the action on the q part by the p part. But that's not that important for us today. So the second thing that you read about in the book is groups of order 12. And with groups of order 12, you can show that either G has a normal Sylow 3 subgroup, or G is isomorphic to A4, which has a normal Sylow 2 subgroup, so this is good. So you're guaranteed, in cases where your group has order 12, at least some normal Sylow subgroup. So G, in which case G has normal 2 Sylow. So this is good. The theme here so far is that we get these normal subgroups. Normal subgroups are very useful because you're often interested in things like simplicity of groups, because that has a big impact on what homomorphisms a group admits. And it also allows you to sort of break down groups if you can say, well, I have a sort of simple quotient or something like this. So anyway, this number has the shape p squared q, where p is 2 and q is 3. So let's consider more generally groups of order p squared q. I'm not going to make any assumption on the ordering yet, so this is more generally. In fact, it turns out it sort of reduces to the case of groups of order 12. The analysis is in many ways much simpler, because what you find is that when you do the calculations with the sort of formulas that tell you a lot about np and nq of g, that things can only go wrong in the case where P is 2 and Q is 3. So you just then refer back to this case. So what's the answer? Well, if P is greater than Q, well, then the formulas for from the Sylow theorem tell you that there must be a normal Sylow P subgroup. And in the other case, you can show, it's not hard, I mean, it's a little more work than this because this just sort of follows trivially, but this case is a little more work, but not too much. Either G has normal Sylow Q subgroup, or P squared Q equals 12, and we're back to this sort of degenerate case where G is isomorphic to A4. And there are lots more cases like this. There are tons more things like this. But again, what's great about these is that they give you these normal subgroups, and that's useful for a couple of purposes. One purpose I've already mentioned, and that is showing that groups are simple or not simple or something like that. Another use is that if you're trying to figure out the structure of a group, often what you can do is break something down into a product of groups, one of them normal, one of them not. And in that case, there's a sort of canonical system of writing these things down called semi-direct products. And so you have this sort of systematic way of understanding all the different groups of small order in terms of Sylow theory and semi-direct products. Anyway, another of the things that we talked about is conjugacy in Sn. So I'll just very, very briefly remind you of what happened there. So we have disjoint cycle decomposition. We have given tau in Sn, if sigma can be written as A11, A1, L1, up through A, K1, AK, LK. This is its disjoint cycle decomposition. Then tau sigma tau inverse is just equal to tau A11, tau A1, L1, etc. So we know how conjugacy works, and in particular, this formula shows effectively that elements of Sn are conjugate if and only if they have the same cycle shape. So elements conjugate if and only if they have the same cycle shape. So this is good. What we're going to do is now sort of combine these sorts of themes, combine this sort of Sylow-theoretic stuff with a study of Sn, or more accurately, the alternating subgroup of Sn. And we're going to find some nice properties. So the first one is in the optional homework assignment. So here, let me just erase this and start by saying notes on A5. So the first case we're going to sort of study that combines the Sylow theory stuff and conjugacy in Sn is, what does A5 look like? We've had some hints of this when we were looking at the geometric stuff, because we found that a particular group that arose as the symmetries of an object looked like something that must be A5, but we never proved that it really was. Well, I'm going to give you a result that does do that. Or at least on the optional homework assignment, you'll find a sort of set of things that lead you through one part of that, and then I'll sort of finish that off here with a converse. So the first main thing you need to know and this is what's on the optional homework assignment, is that A5 is simple. So it's a simple group of order 60. And what I want to do now is prove a converse. So what's this converse? Well, the converse is if G is a simple group of order 60, then G is in fact A5. So we showed that this symmetry group several lectures ago was a group of order 60 and that it was a simple group. So this result sort of finishes it off and tells you that the thing must be A5. But in some sense, this result relies on this result. So it's not entirely complete unless you do the exercises. But this is just sort of, it's just sort of an application of the sorts of things I've talked about so far. So let's start proving the thing. So proof. Well, let's see, a couple of things that are kind of obviously potentially useful. The first one is that, well, n2 of G is congruent to 1 mod 2 and divides 30. And so this gives us sorry, 15, because 2 divides 30. That's utter nonsense. So this thing must be equal to either 3, 5, or 15. And what we can try to do, so a decent strategy is, yeah.
I just want to understand, n sub 2 of G
is the number of Sylow 2 subgroups. N2 of G is the number of Sylow 2 subgroups.
and then just to the right there that says 115.
No. Sorry. What I mean is it divides. Whatever this number is, we know that it's congruent to 1 mod 2, and that it divides 15. This is what the Sylow theorem tells us. So the strategy that I'd like to use is first show that this thing is not 3 by sort of just general tools. Then show that there exists a subgroup of G, call it N, of index 5. Index 5. Now, this should be ringing a bell. I'm using the letter N here, so this will probably arise as the normalizer of some Sylow P subgroup. And the third thing is to do is to use the action of G on the coset space. So if you have some group G, it certainly acts on its coset spaces by translation, by left multiplication. So if this thing has index 5, then if n has index 5, then this coset space has size 5. So I have this group action, this group, and each element of the group is inducing some permutation of a set of 5 elements. And so you effectively have a homomorphism from G to the symmetric group on 5 elements. And it's from that we're going to extract the isomorphism with A5. So I'll explain that in detail later, but this is just sort of a preview to keep you aware of what's going on with the strategy. So, and we'll show that this has, with only even permutations of the coset space. So let's start with the first part of this. So, first thing I claim is, as I said over here, the n2 of G is not equal to 3. So, it suffices to show G has no subgroups of index 5, since if P is a Sylow 2 subgroup, we saw before that the normalizer of P in G must have index equal to n2 of G. And if this thing is 3, then it contradicts the fact that G has no subgroups of index less than 5. So less than 5. It has certainly subgroups of index 5, but none of less than 5. So let's prove this part. So suppose we have a subgroup has no, and I should also say proper or non-trivial, yeah, proper subgroups. So suppose the index of H in G is 2, 3, or 4. Well, then I have an action of G on the coset space. So this is by left multiplication. Now we know that the action of a group on its coset space is by left multiplication is transitive. So that's good. And every G in G induces a permutation of this coset space, G mod H. So in effect, the natural action of G on G mod H gives us a homomorphism from G. You have to verify that this thing really is a homomorphism, but that's not hard. So there's a homomorphism from G to the symmetric group on the coset space, G mod H. So in other words, this takes element G to the permutation induced by G. Now, let's talk a bit about the kernel. So, can the kernel possibly be all of G? Well, consider what's happening here. We have G acting on G mod H by left translation. Now, H is some proper subgroup. So H isn't all of G. We know that if something is going to act trivially on the coset space G mod H, well, then it had better be in H, right? And that's just the sort of definition of the action. Things are equivalent only if they differ by multiplication by an element of H. That's how cosets work. So the kernel must be contained in H just by sort of general principles. It's a normal subgroup of G, which is also contained in H. This thing is a proper subgroup of G. So this thing is not all of G. Moreover, we know something. We had a hypothesis here. G is simple, right? This thing is a normal. So G is simple. What is kernel of phi? It's trivial. The kernel of phi must be trivial. That's the definition of simple. So, what does the isomorphism theorem tell us? Exactly. The isomorphism theorem tells us that phi must be injective. In fact, you don't even need the isomorphism theorem. I can just say that phi is injective. G is isomorphic to some subgroup of the symmetry group on the coset space G mod H. Okay, so why is this a contradiction? Oh, sorry, you're not in the class. So why is this a contradiction? So I have G, a subgroup of sim G mod H. Now this thing just looks like the symmetric group. Exactly. This thing is just the symmetric group on the index of H and G letters. So by hypothesis, this index was 2, 3, or 4. So this thing has order 2 factorial, 3 factorial, or 4 factorial. But G is a group of order 60. It can't possibly fit in there. We have a contradiction. So, indeed, there can't possibly be a proper subgroup of G with index less than 5. And therefore, because the index of the normalizer of a Sylow 2 subgroup in G must equal the number of Sylow 2 subgroups, that number can't be 3, and so n2 of G is not 3. We've eliminated that case. What's good about this, as a sort of first claim, is that it sets us up to show that in a case where n2 is 5, n2 of G is 5, well, we have this sort of natural action going on here, and we can in fact show, wonderfully enough, that that thing is going to have all the same properties as here, in other words, giving an injection into the symmetry group, and we're going to be able to show that all the elements there must be elements of the alternating group. They must be even permutations. And since G has order 60, it's going to have to be the full A5. So let me go through that. So claim 2. n2 of G is 5, and G is isomorphic to A5. So proof. So again, P is going to be some Sylow 2 subgroup. We're going to let n be the normalizer of P and G, and as mentioned several times before, the index of n and G is n2G, which is by hypothesis 5. So we have this index 5 subgroup. And again, we have an action of G on the coset space G mod n. And so again, we have a homomorphism. We have hom phi going from G to sim G mod n, which in this case is isomorphic to S5 because G mod n has 5 elements. And again, same sort of argument over here. Well, we know that no n is proper, so the kernel is not all of G. Therefore, by simplicity, we know that the kernel is trivial. And so we think of G as being really a subgroup of the symmetry group here. Oh, sorry. Yeah?
You say you know n is proper, and therefore the kernel is not equal to all of G. I'm sure that's really simple, but if you could just say why real quick.
So the reason that the kernel is proper as a result of n being proper is the same argument as the one over here. So the idea was, well, let's think about how cosets work. When can I possibly have an element of G which is going to make the action on G mod H completely trivial? Well, the definition of cosets is by this equivalence up to multiplication by H. If I have something outside of H, that's sort of bringing me into a non-trivial coset. It amounts to sort of multiplying by something that shifts me around. The only way I can stay in the same place by multiplying by something is if I have something in what I'm quotienting by. And that's, in this case, H. And in this case, n. So n is proper. The kernel of phi is contained in n. And so the kernel of phi is proper. Does that make sense?
It'll have to.
Okay. Yeah.
So where does the G is contained in S5?
Okay, so again, it's the same sort of argument as before. So the fact that the kernel is trivial tells us that this homomorphism is injective. So the question is, how do we know that the G is contained in S5? So, well, this thing is injective. This thing just looks like S5 because it's a symmetric group on 5 letters. And so we can imagine that G is just a subgroup. We can identify G with its image under this homomorphism. I mean, the G is isomorphic to its image under the homomorphism because it's an injective homomorphism. And so it suffices for us to think of these things as actually just being in S5. It's a notational convenience in some sense. So perhaps I should put this in quotes, but the idea is we think of G now as being a subgroup of S5 because we have an injective homomorphism from G into S5. Yeah?
You can think that it's part of that because since you haven't shown it's a surjective map, then it could be a subgroup.
It's not going to be surjective, in fact. So it makes good sense for us to think of it as being a subgroup, but we can't think necessarily that this thing is actually equal. In fact, we know they're not equal. Why? Well, because by hypothesis, G has order 60, and S5 has order 120. So 2 times that. So they're not equal. Okay. So now let's suppose that G is not contained in A5. In other words, there's some element of G which is not in A5. Well, remember A5 has index 2 in S5. So that implies that GA5 must be all of S5, right? Because we're sort of multiplying by this thing, I get the other coset. So it gives me all of S5. And then by a formula we've seen before, I think that you might have even had to do this on homework. This is sort of one of these sort of index formula type things. In fact, you can show this pretty directly. I mean, you don't need to rely on anything sophisticated. But you can, and that shows that the index of A5 intersect G in G is 2. You can show this directly. It's not a big deal. But this is the most important thing. And that implies the A5 intersect G must be normal in G. Right? Index 2 subgroups are automatically normal. Well, this is pretty important, right? Because what do we know? What do we know about G? Well, by hypothesis, it was simple. This thing is this non-trivial proper subgroup. This is a contradiction. Contradiction to simplicity. So we must indeed have that G is a subgroup of A5. Therefore, G is in fact a subgroup of A5. Now this thing has order 60. And this thing has order 60. Follows that they must be equal. Yay! So we've actually shown that in this case, G is A5, or at least isomorphic to A5. Yeah?
So for that last step, we're pretending we've already proved that A5 is
Yeah, so I mean,
A5 is just normal.
well, I mean, right. So what you need is that you need this thing to show that the thing is normal. Okay? I mean, you know that A5 is normal in G. I mean, it's the kernel of a homomorph. But there is a sense in which there's a bit of an issue with this thing. I mean, this could be, in some sense, a contradiction. I mean, it could be, for instance, that A5 is not simple, and so that I've actually arrived at some sort of other contradiction, which would show, in that case, that N2 of G is not equal to 5. I mean, this could have been a sort of conceivable direction of things. But we have a previous proposition saying that this thing is, in fact, simple, so everything's fine, everything's wonderful. And you can, in fact, show directly that N2 of A5 is 5, so there's no sort of inconsistency or anything here. Yeah?
Just go over again why the index being 2 and 5.
It's normal? Oh, well, so look. So suppose I have something of index 2. H and G is of index 2. I want to show that H is normal. Well, so suppose I take some G and G. Well, and suppose, I mean, certainly if G is in H, then GH equals HG, because that's just H. I'm just getting H back. So, you know, in that case, so if G is in H, we automatically get GH equals HG. But suppose G is not in H. Well, GH is then equal to all the things, because this thing has index 2, is equal to all the things in G that are not in H. I mean, I just sort of partitioned the thing into two pieces. But likewise, the right coset HG is the same thing. It's all the elements of G that are not in H. So these things are equal. GH equals HG. Therefore, GH G inverse equals H. For all G, therefore, H is normal. Great. Oh. Yeah. Oh, yeah, sorry.
You said at the very proof that N2 of G had to be 3, 5, and 15.
Yeah.
You ever deal with the case where it's 15?
Yeah, that's what I'm going to do now. Yeah. Or at least in some abbreviated form.
Wait, so does that argue that all subgroups of index 2 are normal?
Yeah. This shows that any subgroup of index 2 is normal. I thought this was a homework problem or something. No. Yeah, I don't know. I mean, yeah. Anyway, this is definitely a good fact to know. I mean, you should know that subgroups of index 2 are normal. You can definitely leverage this quite often. I mean, it's a very, very, very useful fact. So let me just label this thing. Proposition. Subgroups of index 2 are normal. Proof. There, it's official. Okay. Claim 3. So N2 is not 15. I'm going to actually skip over a lot of the details here because it gets to be a bit hairy. But again, it's sort of one of these proofs by contradiction. So suppose it is. Well, here's a way of putting it. If we can show there exists a subgroup M of G with index equal to 5, then by same argument, as in claim 2. So this is, in other words, replacing n with m. You can show that G must be isomorphic to A5. So that's good. And here's the problem with this. Well, n2 of A5 is 5. You can do this by sort of element counting argument. Therefore, have a contradiction. So how do we construct such an M? Well, I'm not going to go into detail. This is sort of one of these roundabout Sylow arguments where you have to keep sort of like... So here the issue is that Sylow 2 subgroups don't have order 2, they have order 4. So for instance, you don't know that they have trivial intersection. You know that for prime order subgroups. They're either equal or have trivial intersection. That's great. We don't know that here. And in fact, what you do is you take advantage of this fact, but you have to be very careful about it. So what you want to do is, in fact, show that there are Sylow 2 subgroups which have intersection of order 2. And then you can show that its normalizer must have order 5. So let me just write that down. And then you can go home if you're feeling energetic and work out the details. So construction of M, details omitted, but here's the rough idea. Show there exist Sylow 2 subgroups P and Q such that the order of the intersection is exactly 2. So they intersect on 2 elements. And show then that the order of the normalizer of P intersect Q, the order, not the index, must be 12. You do this by just sort of showing that, well, these things must be normal. They must commute with the things in here. And so you end up getting a whole lot of elements. You end up getting a whole lot of non-identity elements in here, but you know that the size must be bounded, so you end up showing that the normalizer must be 12. That's the basic idea. It's just this sort of combinatorial trickery, very much similar to what we've done so far. And this is enough. This M suffices. It has index 5. So that's great. So M is equal to this normalizer of P intersect Q in G. Okay. So that's great. This shows completely that G is isomorphic to A5. So this finishes end of proof that G is isomorphic to A5. So what about AN? So I don't have time to go through this. But what I'm going to do is I'm going to give you a series of sort of statements that look very plausible, and that if you fill in the details for them, you'll actually be able to see immediately that AN is simple. So, theorem. AN is simple for n is greater than or equal to 5. There are a number of different ways of doing this. One way of doing this is very, very computational. I'm going to sort of give you a hint at a different method. So the proof I'm going to suggest is by induction. So A5 is part of the homework. It's optional homework, don't worry. It's, I mean, it's with the usual homework, but there's essentially no homework for next time other than reading. So life is good. But if you're feeling gung-ho about Sylow theory, then there's a wonderful set of exercises in Sylow theory showing that A5 is simple. I also might suggest that going through that before the next exam is very useful preparation. So, I mean, just as a sort of way of testing yourself. I think it's the 24th or something. The next, yeah. I mean, it's on the webpage. There's an E on like a normal class day or something, and that's the date. It's like the 24th, I think. I mean, 24th is a Monday, I believe. So yeah, we didn't want to have it on the Wednesday, the 26th. So okay, so we've done the base case. Now, what about n greater than or equal to 6? So I'm just going to write g equals an because I'm going to want to be able to talk about stabilizers of something. And the usual stabilizer notation is to have a subscript. And I can't have an additional subscript with an an without it looking totally gangly. So I'm just going to let g be an. We're going to suppose, for the sake of arriving at a contradiction, that there is some normal subgroup of G which is neither trivial, neither trivial nor all of G. And so what we're going to do is, of course, because we've been talking about group actions and Sylow theory and stuff, is we're going to use the same sorts of techniques. And the first example of using those techniques is we're going to use the fact that G acts on this set, 1 through n. And we're going to let Gi be, as per the usual notation, the stabilizer of I. So remember, this is an, so of course this does have a natural action on this set. And we can certainly let Gi be the stabilizer. What is this isomorphic to? And what does Gi look like? Exactly. It is an minus 1. Haha. Well, an minus 1 by induction hypothesis is simple. So the crux of this thing is going to be to leverage the fact that we know that the stabilizers are simple. Simplicity is important. So I'm going to give you a series of claims, none of which are particularly difficult to show. And they will prove this. But you have to fill in the details for these claims because we are out of time. First claim is that there does not exist an element of H. So remember, H is this putative, non-trivial proper subgroup, normal subgroup of G. There does not exist tau in H other than the identity such that tau fixes some I. So, I mean, the way that you actually sort of end up using this is, I mean, just sort of to make the connection here clearer, to make it easier to figure out what happens in the next claims. If I know that tau 1 of I equals tau 2 of I, tau 1 and tau 2 being in H, then I know that, in fact, tau 1 equals tau 2, since then, well, so I'll put it this way, implies this, since then tau 2 inverse tau 1 of I equals I. So this thing must be the identity. So tau 1 must equal tau 2. So how do you show this? Well, the simplified version is to show, so the proof of this involves showing that Gj must be a subgroup of H for all j, and then show that in fact, AN, which is generated by all of the GNs, is a subgroup of H. And so AN is, H is all of AN, H is all of G, contradicting the hypothesis that H is proper. So that's a contradiction. So the real point is to show this fact, that every GJ is a subgroup of H. And that's just sort of, it's using the sorts of things that we've done so far. And then the last two things are the following. So claim 2, given tau and H, only 2 cycles can appear in its disjoint cycle decomposition. And then claim 3 is the opposite. So given tau and H, tau doesn't just have 2 cycles. In its decomposition. And the way you show these things is just by taking a putative element and then showing that you have some other element you can get to by conjugating that, showing that that element must have those 2 elements, the conjugate and the original element, must fix or must take a certain element to the same element, and then or must take a certain number to the same letter, and then that's it.